Okay, so today we're going to be looking at recurrence relationships, and these are a type of sequences where the formula for the general term involves the previous term. So I've got an example here, and the formula for the unth plus 1 term, this equals the unth term plus 3. So this is a formula that gives us all the terms in the sequence, but it involves the previous term, so it's recursive. So to get to the next term, you need to know the previous term. And the other bit of information you need is the first term. So to get to the next term, we need the previous term, but we also need to know where we need to start off from. So we have u1, and then from this we can work out u2, u3, all the way up to infinity. So let's just plug in these numbers into the formula and see what the sequence looks like. So we have that the first one is equal to 5, and then u2, let me just do the working over here, u2 is equal to u1 plus 3, and that's just 5 plus 3. So that's 8. So we have that the second term is 8, and then let's do one more. Let's find the third term. So u3, we just plug it in here. So n plus 1 is equal to 3, which means n is equal to 2. So u3 is equal to u2 plus 3. So this is just 8 plus 3, and this is 11. So the third term is 11, and this goes on forever. So we see that at every term, we're just adding 3, and we're starting off from 5. So you may notice that this formula can actually be generated by an explicit formula as well. But recurrence relationships can be a very powerful tool to store all the information in a very convenient way. So sometimes recurrence relationships are simpler than the explicit formula for a sequence, and sometimes there isn't an explicit formula for a sequence. So this is a very nice way to represent all the information, and all we need is a formula involving the previous terms and somewhere to start off from. So let's look at one more example. We'll do un plus 1 is equal to un squared minus 1. So now this formula isn't linear, it's not just adding a constant. We've got the previous term and we're squaring it, and then we're subtracting 1. And the other bit of information we need is the starting point. So we need to know that u1 is equal to 2 in this case. So now we've got all the information we need, and we can plug in some numbers and get a sense of what the sequence looks like. So the first term is 2, and then for the second term we just plug it in. So n plus 1, we let this equal to 2, which means n is equal to 1. So u2 is equal to u1 squared minus 1. And then we just plug in u1, so this is 2 squared minus 1, 4 minus 1, which is just 3. So the second term is 3. Let's do one more. Let's find the third term. u3 is equal to u2 squared minus 1, and this is 3 squared minus 1. That is 9 minus 1, so that's going to be 8. And this is going to carry on forever. Right, and this is an example that you can see that it isn't very obvious to find out the explicit formula, but we've got a very simple recurrence relationship that generates the whole sequence. So now we're going to look at a few examples where we're given the sequence of numbers, and we're going to try and deduce what the recurrence relationship is. Okay, so I've got 4 sequences up here, and feel free to have a go at yourself, trying to work out what the recurrence relationship is. We're going to work through one by one. So for the first one, we've got 3, 5, 7, 9, and you can see that at every next term we're just adding 2. So the relationship is that we take the previous term and we just add 2 to it. So the recurrence relationship is going to be un plus 1 is equal to un plus 2. And we also need the first term, so u1 is equal to 3. And this is all the information that encompasses this sequence. So that's quite an easy example because we're just adding a constant every time. Now for this sequence, the terms are getting smaller every time, but in fact they're getting smaller by an exact ratio. So we've got 125, so we're dividing by 4 here, then 25 to 6.25, we're also dividing by 4 here, and to the next term we're dividing by 4. So the pattern here is we're dividing by 4 for every single new term in the sequence. So the recurrence relationship is going to be un plus 1 is equal to un divided by 4. It's as simple as that. And then we also need the first term, so u1 is equal to 100. Okay, so now this one's a bit trickier because we've got 2 operations at play. If you look at the pattern, we've got 0 to 1, then 1 to 2, 2 to 5, and 5 to 26. So the jumps aren't constant. What we're actually doing is we're squaring the number, and then we're adding 1. So 0 squared plus 1 is 1, 1 squared plus 1 is 2, 2 squared plus 1 is 5, 5 squared plus 1 is 26. So this is a pattern, and we can write this mathematically as un plus 1, so the next term is equal to the previous term squared plus 1. And then we also need the first term, and that's just 0. Right, for the last sequence, this is a very interesting sequence, very famous sequence. This is called the Fibonacci sequence, and you may be familiar with. So this has a very nice recurrence relationship, and the pattern here is that we take the previous two terms and we add them together to get to the next term. So 1 plus 1 is equal to 2, 1 plus 2 is equal to 3, 2 plus 3 is equal to 5, 3 plus 5 is equal to 8. So the pattern here, we can write this very nicely mathematically, is un plus 1 is equal to 2un plus un minus 1. And this is a recurrence relationship that involves the previous two terms. So now we need not only the first term, but the second term as well. So we need to declare that u1 is equal to 1 and u2 is equal to 1. Because if we want to find out the third term from this formula, we plug in n plus 1 is equal to 3 here, so u3 is equal to u2 plus u1. And that's why we need both these two terms to start off with. So as you may know, the Fibonacci sequence appears everywhere. So you see it in nature, you see it in seashells, you see it in flowers, and you can model populations using this sequence. It's very useful. And another nice property, it's got a very nice recurrence relationship. And the explicit formula for this is actually quite horrible. It involves square roots and powers of n, and it's not very easy to deal with. But this formula is very nice. We're just adding the previous two terms to get to the next term. So this kind of shows how powerful recurrence relationships can be.